Now, what's next? One burner versus 3 to 4. Well, this is kind of a little bit of a tangled web, and this video is going to serve as an educational piece for our sales team as well, right? And so, why do the competitors have 3 or 4 burners? Why do they have 4 or 5, or in some cases even 6 glycol pumps? Well, I'm going to tell you why. And it all stems from a decision to have glycol jacketed lines. So I might not cover all of this in exactly the same order, but Anthony's just showing you there that there's one burner on the truck, not 3 or 4. And if I look at the converse, I'm sure that you out there in plural component land recognize these little Webasto heaters, and they're using these heaters to heat the individual circuits of white, yellow catalyst. Now, the reality is that the Aero trucks, the Endosys trucks, the MRL trucks, you know, Endosys uses electric primarily to heat, but the other guys are using glycol jacketed lines. You have a high pressure line that is buried within a hose that is carrying glycol, right? And they're using that to try to maintain the temperature inside that high pressure material lines. And this gives you, that's a great image there, thank you, Anthony, that shows you kind of what a cluster it turns into, because you've got a high pressure line coming into the resin side, a high pressure line coming into the material side, and then you have glycol flowing down through that hose and then being returned somewhere. Now, eventually, it's not if, it's when a high pressure hose blows. That resin or that catalyst will be transported through the glycol and into whatever glycol reservoir tank, or whatever glycol pump, or whatever glycol burner heater, okay? That material is going to travel through those lines. In fact, which hose blew? You know that you lost material pressure, you know that it was a yellow material pressure, so that narrows you that you've lost pressure to a yellow, one of your yellow hoses. But you don't know which one. You've got to go on a fishing expedition because the material is leaking inside your glycol, okay? Now, if that happened today and tomorrow you blew a catalyst hose, high pressure hose, and those glycol circuits were mixed, right? Then you would have a really big fat mess inside your glycol circuitry, right? And this is why those circuits are separated, and you have a different heater and you have a different pump for every one of those circuits, so that you don't have the possibility of your resin and catalyst mixing inside of a glycol circuit.
But then you now have 4 or 5 pumps to maintain, to service, to replace.
And not to mention all of the conglomeration of lines, which, by the way, makes it very difficult to see your guns. And if you notice, by contrast, the really uncluttered view of our guns and circuitry, just a whole lot less clutter coming to those hoses. So wait, I know the question is coming, is how do you get by without having any glycol jacketed lines? Well, we'll get to that in just a moment. I'm just concerned that I'm in some of these things are so tangled together that it's difficult to follow steps. But let's try to let's see if we can go back here to one burner versus 3 or 4. Well, that's what we've been taught. How are we doing that? Well, how we do that, and I think that the guys will insert some B-roll here that shows you've got one glycol pump, and here you see an actual picture of the pump. Very small, pumps 30 gallons a minute. That glycol pump then feeds a manifold, and here I have a picture of the manifold. It's directly up here. Off of each of those manifolds, there's a 12-volt actuated ball valve. That ball valve opens and closes the feed to the heat exchanger. Now the heat exchanger is where ultimately your material is picking up its heat. Your glycol is flowing through the shell side of that heat exchanger. Your material is flowing through the tube side of that heat exchanger through all these small tubes. And as it travels, it's picking up the heat it needs to arrive at temperature. Once that set temperature is arrived at, that ball valve shuts off, which then stops the migration of heat from your glycol into the material. So we're doing this, you wouldn't know to ask, but you might ask, well, what is the overshoot and what is the undershoot of that material? Well, the overshoot would be how far over, once that glycol shuts off, is the trajectory of your material temperature such that you end up overshooting the set point of the material? And the answer is typically yes, but it's only a couple of degrees. So 2 or 3 degrees, you can anticipate that. And if you want your material at 140, well, you're gonna set it at 137 if you already know that your overshoot is 3 degrees,
Yeah.
right? So you can accommodate for that.
If your system didn't have that safety shut off, what happens to the material if you overheat it?
Well, all sorts of bad things can happen if you overheat your material. We've actually seen that the material can coagulate and do funny stuff and go from being a solid to forget the exact word they use, but basically it sets off and begins to form little hard clumps. Okay. When you don't intend, you haven't mixed catalyst with it yet. So you don't want to overheat your material. Also, your pressures will come way out of alignment because this typically, well, let's say the most common mixture, we can do about any mixture you want, but 2 to 1 is the most common. So if your catalyst is really overheated, too hot, it's going to flow like water. You're going to have more volume going through that nozzle than you want and less pressure, right? So it's important that the consistency, the viscosity of the catalyst and resin on a plural component system, you know, they're being forced through these little eensy beensy tiny nozzles, and it's important that they be consistent with each other. Okay. So doubling back then to, you know, we covered far less clutter and plumbing associated with you know, one glycol pump instead of 4 to 6. And another really big advantage is that we have hog pumps that are feeding the high pressure pumps. Now, when I first set about to do this, I went around the country, I asked customers, how often, like what percentage, if you were to pin the tail on the donkey and give me a percentage of time, how often are your high pressure pumps being used to recirculate for heat up? And what percentage of time are they actually pumping material to the road? And, you know, I guess just doubling back a little bit, this stuff does require heating, right? And some of this conversation does assume some basic background knowledge in epoxy, but typically we're heating this product, well, we actually recommend quite a bit higher temperature than some of the other folks out there, but we've been experimenting heavily with it, and for us, 145 degrees on the resin and maybe 140 on catalyst. Somewhere around there. We've studied the viscosity charts and works well, can spray at a much lower temperature. We're spraying, a much lower pressure. While other folks out there might be spraying at 2,800 to 3,000 PSI, we're spraying at 2,200 PSI. Great atomization, great distribution, no fingers, and accelerated hard time. We've discovered that the hotter we heat the material, the quicker the material hardens and the quicker traffic can run over it without making a mess of the white, yellow lines on the road, right? So in one sense, hotter is better. And so, but using hog pumps to feed the high pressure pumps, that 70, whereas competitors are using their high pressure pumps, 70% of its life is being spent to recirculate material. We would estimate that ours is just about 85% of the time our high pressure pumps are running, they're putting material to the road. So that is a enormous benefit. How is that possible? It's facilitated by the hog pumps that are feeding, they are being used to recirculate that material that comes out of the tank, into the hog pump, out of the hog pump, into the heat exchanger, back into the tank, and it just sits there and goes round and round and round. Now, that high volume, low pressure pump also eliminates the need for mixers on top of the tank. And for those of you out there who are familiar, you'll recognize this very quickly. On the tops of traditional trucks, you have all this apparatus that is needed to mix and to draw the material up and over for heat exchange purpose. And all this apparatus is not necessary on the top of our tanks. There is no such apparatus, even in the vertical trucks. I think I have a good, pretty clear picture right here, just scrub part way through, and we'll look at the accessibility around these pumps. Well, once you pressure feed the pumps, you can put the pumps anywhere you want. You can put them up on the roof. On the top of the tanks, there's no agitators, mixers necessary. You can get at all of your, notice how accessible even the accumulators. Notice how accessible the accumulators are when we turn around here and look. Every one of the accumulators is right out there within reach. Pressure gauges, pressure manifolds, high pressure filters, all extremely accessible. And even your hog pumps, for that matter. Look how open and airy and accessible those hog pumps are. You know, if you contrast that with some of the images that you find over here, whether it be on top of the tanks that you can see, or whether it be this pretty, you know, extensive apparatus and moving augers and things down inside of your material tanks. There are no moving parts inside of our material tanks. I want to make that clear to the viewer. No moving parts at all. Whereas, you know, one of my men was out on a project recently where something failed inside of one of these tanks, and there was two guys covered head to toe with epoxy resin. And then this kind of view inside the tank, you know, once you start putting moving parts down inside this, it becomes very difficult to ascertain what's wrong. You can't see it. Touching it is very messy and time consuming. And then there's just some other apparatus here that I want to just show right quickly, which is, you know, the parts cabinet where a lot of this stuff is buried inside of. You know, 100% of our components are out in the open where you can reach them. Look at these accumulators buried down inside of the dark recesses of this cabinet where, you know, they're just very, very difficult to get at and to reach. You know, while I'm here on this image, I want to just point out another feature, because these are called Whitey valves or swage lock valves. They're basically on-off valves. But, you know, in the hydraulic, in the systems that I've seen out there, and again, from Endesys, from MRL, from Aero, you know, they have these three-way valves, and inside these three-way valves, they place a nozzle inside of this, if you were to disassemble this, one way is wide open, and the other way, they turn it, and they have a nozzle, a very small nozzle that is equal to the nozzle that's at the gun.
Okay.
So let me see if I can make this clear. So during a heat up process, they'll turn their hydraulic pressure way down, and so that the pumps move very slowly. Okay. And they will open this ball valve so that the material need not flow back through this little tiny nozzle. Instead, when put in that direction, the material flows through a nice big hole, right? And so it can flow very easily through that nice big hole instead of at a cold temperature being forced through the nozzle. You can imagine how much force it would take, right? Smart move. So now, when the material gets up to temperature, of course, they need to ramp the hydraulic pressure that it takes to create that 2,800, 3,000 PSI, right? So how are they going to do that without actually spraying out to the road? Well, they put a nozzle in the other side of this ball valve, and I hope the viewer can see my finger pointing here. So when you turn that ball valve to off, it is actually flowing through a nozzle, the size of which would be equal to the same size that the nozzle is coming out the gun. And now they can set their pressure.
Okay.
So that's all the time we've got left for segment number 2, and we'll see you back in a few minutes for continuation of segment number 3.